So here we also apply the Gauss law for spherical symmetry. Okay, so actually here is called the shell theorem in chapter 21. I'm not sure whether you still remember it. Actually, during this chapter 21, I just told you what is so-called the shell theorem. There are actually two statements. One is saying that, here we have a shell with a uniform charge on it, and then it tells you if you are outside the shell, then it will feel like all the charges are distributed at the center. Okay, this is the first statement. And then the second statement is that if you are inside the shell, then there will be no E field. Okay, that time I just told you, these are the two statements for the shell theorem. And then at that time I also tell you that here after we know the Gauss law, we can try to verify why the shell theorem is correct. Okay, so let's see. So a shell theorem of a uniform charge attract or repel a charged particle that is outside. Okay, so the key word is outside. Of course, uniform charge is also a key word. Okay, so the shell, as if all the shell charge were concentrated at the center of the shell. So here it says for the shell, the total charge is small q. So it tells you that it is like all the charge are at the center. If it is at the center, it will be very easy because it is just a point charge. So for every point, just say this point, then you only need to know what is the distance between this point and that point. Okay, so maybe R, or maybe this point on the S2. On the S2, this is for S2. Okay, so sorry. Okay, so applying Gauss law to the surface S2. Okay, so for example, this one. Okay, so the radius is let's say small r. So for which small r is larger than capital R. Capital R is the radius of the shell. So which is this one. Okay, so we would find that E will be 1 over 4 pi epsilon naught times Q over R squared. So this is nothing but a point charge. Okay, why? If we apply the Gauss law for this one, we can really have epsilon naught integration of E dot dA equals Q enclosed. Q enclosed is actually Q, okay? Except Q, there are no any other charge. So this is Q. And on the left side, epsilon naught is epsilon naught. And then E will be uniform on the shell because charge density are also uniform. So this is E, a constant E. And then the surface area of the shell is 4 pi r squared, if you still remember. Okay, E equals Q. So we just move all the things over, and then finally we will get E equals 1 over 4 pi epsilon naught Q over R squared. So no matter how large this small r is, as much as this is larger than capital R, then we always get this expression. Okay, so this is the first statement for the shell theorem. And then for the second statement of the shell theorem, it says if a charged particle is located inside a shell of uniform charge, there is no electrostatic force on the particle from the shell. Okay, so there will be no inside, and then uniform charge. Okay, there will be no electrostatic force. Okay, the reason is here we have S1 as the surface Gaussian surface, I mean. So here we apply the Gauss law to S1, and then here we have a R which is smaller than capital R. Here we have R smaller than capital R. For that one, we have R is larger than or equal to capital R. Okay, so here R is smaller than capital R. So in this case, there will be no enclosed charge, which means that for the Gauss theorem on the right hand side, it will be 0. Okay, epsilon naught is not is a non-zero constant. So it turns out that this surface integral should be 0. And actually this is uniform. It is like e times 4 pi r square will be 0. Okay, this is not 0, so e will be 0. So that's why inside the shell we have E field equals to 0. All the things will be cancelled perfectly. Okay, so based on the Gauss law, we can really know why the shell theorem we introduced in chapter 21 are correct. Is correct. Okay, actually the two statements are correct. Okay, so yeah, so a bit like that. Okay, so here we can also apply Gauss law for another case of spherical symmetric. Okay, just now we only have a conducting shell with uniform charge. Okay, no matter whether it is conducting or non-conducting, is fine. Here we mentioned that this one will be a non-conducting sphere. It will have uniform volume charge density. It will have uniform volume charge density. So the whole sphere, okay, the charge will distribute over the whole sphere. Okay, it's a sphere in 3D. Okay, it only draw it in 2D, but actually it's a 3D sphere. Okay, 球体. Okay, so yeah, so the charge not only distribute on the surface but also inside. So in that case, I will also mention that this is non-conducting. This is non-conducting. And then after saying that it is non-conducting, and then I will say the charge can go to elsewhere. So the charge distribution must stay forever. Okay. So yeah, so here we have inside a sphere with a uniform volume charge density. Okay, so here this volume charge density, we call it rho. Okay, so here we have a lambda, sigma, and rho. Okay, so this is linear. This is linear charge density. This is surface charge density, and then rho is volume charge density. Okay, so all of them are charge density. Okay, as much as this linear charge density multiplied by a length, it will become a charge. Surface density multiplied by an area, and then it becomes a charge. And then a volume density multiplied by a volume, and then it becomes a charge. Okay, so here, this is a volume charge density, rho. Okay, rho will be the total charge amount will be small q. Okay, so enclosed charge is small q, which means the total charge for in the sphere. Okay, so q over the volume. Okay, surface area is 4 pi r squared. So for the volume, it will be 4/3 pi r cube. Okay, hope you can remember it. I think it is something like the high school mathematics. So 4/3 pi r cube is the volume of a sphere. Okay, so here we also try to find the E field inside and also outside the sphere. If it is outside, it is very easy. It is nothing but this expression, because if you try to draw a Gaussian surface with a larger r, than the radius of a sphere, then the Gauss law will look like epsilon naught integration of E dot dA equals Q enclosed is nothing but Q. Okay, it's nothing but Q. Okay, on the left side it will be the same as the previous page, epsilon naught times E times 4 pi r squared. So yeah, it turns out to be the same expression. And the tricky part is when we consider the E field inside the sphere. So here we try to imagine there is a Gaussian surface with a smaller radius than the radius of a sphere. Okay, so this is the Gaussian surface we will seek for. Okay, so here for this Gaussian surface, we will also try to find the Q enclosed. So the Q enclosed, so far we don't know yet, so we just denote it as Q enclosed, and then we divide it by the volume. Okay, this is the charge divided by the volume, so this will be the volume density. Okay, so this is the whole sphere, but here this is part of it, and as much as the volume charge density is uniform, which means that the whole part should be the same as this part. Should be the same as this part, no matter how large this R is. But for different R, of course, this Q enclosed is different. Here we just assume R to be a variable. So we have Q enclosed over 4/3 pi R cube. So this is small R cube. This is capital R cube for the whole sphere. Okay. So here we get this expression if we know the volume charge density is uniform. Okay. Later on we have an additional example, and in that case the charge density is not uniform, and then there will be some crazy mathematics there. Okay, so here we can come up with the expression of a Q enclosed by moving this term to the left side, moving this 4/3 pi R cube to the left side. Okay, and of course we can actually cancel 4 pi over 3 on both sides, and then we move this R cube to the left side. So Q enclosed will be Q times small R cube over capital R cube. Okay, so this is Q enclosed. And then applying Gauss law to this Gaussian surface, okay, the left side is actually the same thing, epsilon naught times capital E times 4 pi R squared, nothing special. And then Q enclosed is this one. So we just plug in this one here. And then finally, we can just move over this term and this term over. So we will get 4 pi epsilon naught here, and then R squared partly cancel with this one. So R squared will be partly cancel with this R cube down to an R. So we have Q times R in the numerator, and then we will have R cube in the denominator. Okay, so finally it turns out to be like this. So when we consider the E field outside it, E is inversely proportional to R squared. Okay, all other thing you consider is as a constant. If you don't change the charge, okay, it will be inversely proportional to R squared. But here inside the sphere, this E is proportional to R. Is proportional to R. Okay, so on the next page, we can try to draw it out. So for outside the sphere, we have this expression. R is larger than or equal to R. And then inside the sphere, E is K times QR over capital R cube. Okay, so yeah, so for this part, as I mentioned, this is proportional to R. So it's like a straight line. This is a straight line, so this is proportional to R. And for this one, this is proportional to inverse proportional to R squared, or proportional to 1 over R squared. And if you plug in small r to be capital R on both equations, then you can see they are at the same point, which is this one. Okay, which is this one, Q over 4 pi epsilon naught capital R squared. Okay, which means that if here is the R axis, and then it increase until capital R, and then it start to decrease like this. Okay, any questions? Okay, so this is the additional example. Okay, so yeah, this is one of the if you have brought the textbook, this is one of the problem, the exercise there. I mean the problem 11. Okay, this will be the a difficult one, a difficult one. So I just show you a bit. Yeah. Yeah. So here it says the volume charge density of a solid non-conducting sphere of radius capital R varies with the radial distance R as given by rho equals this thing. This is a constant times R and then divided by capital R. Okay, so yeah, so the SI unit matches. Okay, so this is let me see. I think this value we can just denote it as a rho S and then times R over R for the whole thing like this. So rho S is actually 35.4 picocoulomb per meter cube. Okay, so this is so-called the volume charge density, and then this I mean this one is the volume charge density, and then this is a constant, and then yeah, this will be the density on the surface. Okay. Okay, so it asks you what is the sphere's total charge. This is what is the sphere's total charge. For the sphere total charge, we actually need a triple integral. Need a triple integral. So the total charge amount, let's denote it as a capital Q. Okay, so it will be a triple integral for the sphere, and then for the rho, dv. Okay, v means the volume. Okay, so we have a triple integral. Okay, so fancy thing. Yeah, so you can imagine we need to integrate for 3 variables. Of course, this is a sphere. You can choose different coordinate system, like for example a Cartesian coordinate will have x, y, z axis. But if you really use the Cartesian coordinate, it will be difficult to calculate. For example, if you learn how to calculate the area of a circle in calculus class, you will probably, if you use the Cartesian coordinate, it will be like the area will be 2 times integration of a negative r to r, and then square root of r squared minus x squared dx, something like this, right? When you learn the calculus class. And then you need to do some change of variable, like x equals r times cosine of theta, and then you plug in and then do some change of variable, and then it takes many steps to do so. And here the case is similar. If you really need to integrate for a sphere in Cartesian coordinate, dx, dy, dz, it will be also complicated. It will be something look like r squared minus x squared minus y squared, something like that. Okay, so here, rather than using the Cartesian coordinate, we will use something called the spherical coordinate. Spherical coordinate. Of course, there is still another coordinate system called the cylindrical coordinate. But here we don't use this. So there are 3 types of coordinate system that will be mentioned in the calculus class. So the first one, of course, the Cartesian coordinate, you're most familiar with, 直角坐标系. And then this one is a spherical coordinate, is the 球坐标, 然后 cylindrical coordinate is like the 椭圆, 圆柱坐标. Okay, so we'll use the spherical coordinate. So what is this dv for the spherical coordinate? Or maybe let me try to simply mention what is a spherical coordinate. So it will try to use 3 variables one is r, one is theta, one is phi to represent a point. Okay, if it is in Cartesian coordinate, you will use x, y, z to represent a point in the space. Okay, so maybe if it is a 1, 1, 1, so that point will be something like here, which will be 1, 1, 1. But if it is so before going to spherical coordinate, maybe one thing you're familiar with is a polar coordinate. So for the polar coordinate, it will use r and theta to stand for a point in the plane. So if the radius is r, this angle is theta. So we use r theta to represent a point on the plane using the polar coordinate. If you really need to transfer it back to the Cartesian coordinate, so the x will be r cosine theta, and then y will be r sine of theta, something like that. And then for the Cartesian, for the spherical coordinate, it uses one is the radius, one is a theta. So these two variables are similar, and also another angle called phi. So if you are interested in it, you can simply try to Google it, maybe spherical, S-P-H-E-R, spherical, okay, sphere of inference. Okay, actually I'm playing the aerodynamic games. This one. So for the spherical coordinate system, it is something like this. Okay, so this is r, this is theta. The theta is the angle between this line and the z-axis. And then if you try to project this point on the xy plane, okay, phi, this phi, I just wrote a circle with a bar. So here is another style. So if you try to project this point to the xy plane, okay, and then you try to connect this point to the origin, so this angle between this line and the x-axis will be phi. So when you try to convert the spherical coordinate with the xy coordinate, it will be look like this. So for z, it will be r cosine theta. For xy, rather than we have a r sine of theta, we still have another cosine phi sine phi, something like that. Okay, so here we have dv. You may consider whether it will be dr, d theta, d phi, and get the job done. The answer is no. When you consider the polar coordinate, when we have dA, it will be something like r times dr, d theta. The dimension should be correct like this, because this is an angle. This is an angle. So for polar coordinate, it will be something like this one. Okay, so this is dr, but this one should be r times d theta to become a length. Okay, so for spherical coordinate, I'm not really sure whether we have the Jacobian here. Yeah, we have the Jacobian here. So the Jacobian will be no. Here. Okay, here we can see we have r squared sine of theta dr d theta d phi. Okay, so this will be the dv. Okay, don't worry about. Don't need to worry too much about this. I will not ask it in the exam. So yeah, just let you know a bit about that. So here we can have integration of triple integration, and then this rho is this thing. So this is a rho s times small r over capital R. So we just plug in this one there, and then this dv will be r squared sine of theta dr d theta d phi. Okay, just mention. Okay, so we need to determine the lower and upper bound. So for dr, it will be from 0 to capital R. And then for d phi, it will be from 0 to pi, 0 to pi. And then for d phi, it will be from 0 to 2 pi. You may ask, oh, why this is not 0 to 2 pi, only from 0 to pi? Because that angle is between, okay, this angle is, this theta is between this line and the z-axis, this angle and z-axis. So minimally, it will be like this, is 0 degree. The maximally, it will be like that, 180 degree, cannot go larger than 180. So the upper bound will be pi rather than 2 pi for this one. Okay, so this is a triple integral, looks very horrible, but actually not. This will be extremely easy. Okay, so here we can see that this is a constant, so we can just put it out. So we have rho s over capital R on the outside. And then here, these are so-called, we can separate the variable, which means that this is a function of R, this is a function of theta. They are multiplied together so that we can just separate them. So we have dr here, so we have dr, and then we put the function r inside. So we have r times r squared, we all together have r cubed from 0 to capital R. So this integration is easy. And then for the next one, d theta, we have sine of theta, okay, from 0 to pi. And then at last, we have d phi. You cannot find a phi there. So this function is nothing but a 1. You can write 1 there times d phi, or you can just ignore it, or you can just write it like this. Okay, so it will be easy. Okay, so then here everyone will be easy. This one will be nothing but r to the 4th power over 4. This one, the integration of sine of theta will be negative cosine of theta. And then you plug in, evaluate from 0 to pi. Okay, cosine of pi will be -1. Cosine of 0 will be 1. So this one will be 2. And then this one, integrating 1 will be 5. And then evaluate from 0 to 2 pi will be nothing but 2 pi. So we just have these 3 terms multiplied by this term. So finally, we only have pi times, so this is rho s over r, okay, multiply by this one, multiply by this one, multiply by this one. Okay, so this 4 will be cancelled with these 2 and these 2. And then finally, we have pi, and then rho s, and then r cubed, because this r will be cancelled with this one to be r cubed. So pi rho s r cubed. Okay, this is the answer. And then finally, we can just plug in the number. Pi is 3.14, and then times rho s is this number, 35.4 times 10 to -12. Pico is 10 to -12. And then times r, capital R is 5.6 centimeters, 0.056 cube. Okay, so finally it's 1.95 femtocoulomb. Femto is 10 to -15. Okay, so this is the answer to the first question. Okay, I do not pick it as a selected problem. I just saw it here to let you know. Yeah, maybe if you learn the multi-variable calculus later, then you'll be able to understand better. But I will say it is not a very complicated multi-variable integration, but yeah. But at least you need to know what it is. Okay, so for the question B, it asks what is the field magnitude E at R equals 0. So this is give you a rest because R equals 0 will always be easy. It will say that E is 0. Okay, and yeah, that's it. Yeah, because if you don't trust, then you can imagine, oh, we have a sphere there. Then you can try to draw a Gaussian surface, which is just a dot. So the enclosed charge should be 0. Okay, so you will finally get E to be 0 there. And then R to be capital R over 3. Okay, so this is not easy. Because we need to recalculate Q enclosed again. So I do not go from scratch, because here we need to assume that this is the sphere, and then we should have a Gaussian surface inside it. So this is the original sphere. SPHERE, the sphere for the bigger one, and then the Gaussian surface is inside, because here R is only 1/3 of the radius. Okay, so here we have a Gaussian surface inside, and as much as we need to apply the Gauss law for this Gaussian surface, so we need to calculate the Q enclosed. So we don't integrate from 0 to capital R. Rather than that, we integrate from 0 to small r. So the only difference is that we only integrate from 0 to small r. So all the other thing will be the same. So here will be small r to the 4th power over 4. So this small r can't cancel with this capital R. This is the only difference. So I do not repeat from the beginning. I just tell you that Q enclosed will be the same terms, rho s over capital R, and then the integration of R cube dr. Here we only integrate from 0 to small r. So here we have r to be the same. So let's denote it as r prime, so that this r prime and this r, you can distinguish them. Okay, and then similarly d theta for sine theta from 0 to pi, and then d phi from 0 to 2 pi. Okay, the same thing. Okay, so this is r to the 4th power over 4, and then this is 2 pi, and then multiply together, multiply with rho s over r. Okay, so similarly 4 and 2 cancel, and then this small r and this capital R can't be cancelled. So it turns out to be pi rho s r to the 4th power over capital R. So this is Q enclosed, and then we can apply this is Q enclosed, and then we can apply the Gauss law. So this is epsilon naught integration of E dot dA. Okay, so as always, it is epsilon naught times E times 4 pi r squared. Okay, so we have this one equals to this one. So we can just move over this term or make necessary cancellation. So this r squared and r to the 4th power cancel down to r squared. Okay, all the other things, still this one. This pi and this pi can be cancelled. Okay, so finally we can have E equals, let me see, 4 epsilon naught capital R. So we have this one, and this one in the denominator, and then finally we have a rho s and r squared in the numerator. So this is the expression when r is smaller than capital R. Okay, so here in this question we need to evaluate r at capital R over 3. So here we can just plug in r equals capital R over 3. So it becomes rho s times capital R over 3 quantity square over 4 epsilon naught capital R, and then do the cancellation. It becomes 36 epsilon naught R square and R can be cancelled. So it turns out to be rho S capital R. And then we can plug in the number. Rho S is still 35.4 times 10 to negative 12 rho S. And then R is 5.6 centimeters, 0.056 over 36 times epsilon naught, 8.85 times 10 to negative 12. Okay, so this number is 6.22 times 10 to negative third power Newton per Coulomb. Okay, so this is the answer to question C. Question C. Okay, this expression we will use it in the final one. Graph E versus R. Okay, finally we will use it. Okay, so here it also asks you R equals to capital R. But yeah, actually we can directly calculate it, but here we would like to come up with the expression when R is larger than or equal to capital R, because it will be useful for question E. So here we have the sphere. This is the sphere. And then we also define a Gaussian surface to be larger than it. So this is the Gaussian surface for this part. Okay, Q enclosed, we don't need to calculate again because this is the capital Q we calculate at the question A. We already know capital Q. Okay, so we don't need to calculate again. So Q is pi rho S times capital R cube. Okay, equals epsilon naught E 4 pi R square as usual. Okay, then we can do cancellation. This pi and pi can be cancelled. Okay, and nothing else. Then we can move over this epsilon naught and also R square and also this 4. So finally, we will get E to be, we have 4 epsilon naught R square in the denominator. 4 epsilon naught R square in the denominator. And then we have these two terms in the numerator, rho S R cube. Okay, so this expression is for R is greater than or equal to capital R. Okay, but of course this question, it asks you R equals to capital R. So we can just plug in R equal to capital R. So it turns out to be rho S times R cube over 4 epsilon naught, and then R square to be a capital R square, so we have a capital R square. Okay, so we can cancel this R square with the R cube. So it turns out to be rho S over 4 epsilon naught. Okay, so we can plug, I still forgot the capital R here. Okay, so here will be rho S 35.4 times 10 to negative 12, and then times 0.056 meter. And then over 4 times epsilon naught 8.85 times 10 to negative 12, like this. Okay, so this number is 5.60 times 10 to negative 2 Newton per Coulomb. Okay, so this is the answer to question D. Okay, and finally we can draw the graph for part E also. Okay, so here we try to recall E to be rho S times small r square over 4 epsilon naught R. So this is what we get it in part C. For R is smaller than capital R. And rho S times capital R cube over 4 epsilon naught small r when R is larger than or equal to R. Okay, so for the upper one, it is proportional to R square. Proportional to R square. This one is inversely proportional to R. Okay, so this is different from that case. Different from this one. Different from this one. For this one, the charge density is uniform over the whole sphere. And for this one, it is proportional to the radius. So this is proportional. This is proportional to the radius. Proportional to the distance radial distance. Okay, so in this case, okay, so this one is proportional to r squared. This one is proportional to 1 over r. It's just like multiply by r. For that case, it's proportional to r, proportional to 1 over r squared. Okay, but yeah, maybe just a coincidence. So don't try to remember that like that. Okay, so finally, if we try to plot the graph, it will be like this and this. Okay, so this is capital R. The x-axis is R axis, and then this is E, and then Newton per Coulomb. So for the middle point, this is 5.6 times 10 to negative 2 Newton per Coulomb. And then for this part, E is proportional to R squared. For this part, E is proportional to 1 over R. And this is pretty much it. Okay. So this additional example is quite complicated. At least the mathematics is quite difficult. So yeah, so